Okay, today our topic is symmetry. So we've been talking about different kinds of transformations, and some of those, you may have noticed, create different symmetries in the original shape and the final shape. So we're going to go through some different types of symmetry today. We're going to start off with line symmetry. So line symmetry is when we take a shape and we mirror it over a line, and we end up with the same shape on the other side of that line. So we have basically a shape we could split down the middle, and it's going to be the same on both sides. So if I kind of took a shape like we've been talking about, I took this triangle and I mirror it across this line, I'll end up with a triangle over here that should be congruent because reflections create congruent shapes. They're an isometry. So what I end up with is a big triangle here, and it's going to have a line of symmetry down the middle that splits the two even halves. So let's look at some examples that are already drawn so I don't have to try to draw them myself. So here we've got a bunch of different shapes. If you want to pause the video and try to answer this question, go through each of them. Think about, does it have any line symmetry? And if so, does it have more than one line of symmetry? Where are the different lines of symmetry for each shape? So if you want to try it on your own, go ahead and pause and try that, and we'll go through the answers here. So number one, it does look kind of symmetric. So it looks like there's something going on there that's repeatable, but I can't find any spot where I could cut through the shape. So say I cut through it right here. The left and right half are different. No matter where I cut through it, I can't make two identical shapes on either side. So there is no line of symmetry in this shape right here. The second one, the left and right half look identical. So if I split it down the middle, then I have one line of symmetry for this shape. If I tried to split it anywhere else, I'm going to end up with two uneven things. This third one, this looks like an equilateral triangle. So all three sides look to be the same, meaning I could split it straight down the middle here and end up with two identical triangles on the left and right. However, I could also split it from this corner through this side and end up with two identical triangles there, or through this corner to this side and end up with, let me erase that one, erase that, and end up with two identical triangles here on the upper right and lower left. So we actually have three different lines of symmetry for this equilateral triangle. So number 3 has 3. Number 4, I could split right there. I get two equal rectangles. If I split it this way, I would have gotten the same two equal rectangles since this is a square. I could also split it along the diagonal, and I would end up with two triangles that are congruent. Or this diagonal, I would end up with two congruent triangles on the top right and lower left. So there are a bunch of lines of symmetry here. It looks like we have a total of 1, 2, 3, 4 lines of symmetry for a square. Number 5, similar to number 1, looks like there's some kind of pattern going on here, but it's not going to have a line of symmetry. If I cut right down the middle here, this actually is not the same left to right, right? Like I have this nub here, but no nub here, and on the bottom it's the opposite. So no lines of symmetry on number 5. Number 6, I could split right down the middle this way. I end up with two equal, I guess those are parallelograms, two equal parallelograms there. Let's think if there's any others. If I go corner to corner like I did on the square, then I'm going to end up with two congruent triangles, but they're not a mirror image of each other, meaning that that is not a line of symmetry. We can't reflect over that line and end up with the shape, this total shape. Same thing for the other diagonal. We get two congruent triangles, but they are not going to be mirror images of each other. Likewise, if we cut through the middle here, we're going to end up, let's see, here we end up with two congruent shapes as well, but again, it's not a mirror image. If I went across with this point, I don't find my matching point over here. It's shifted down into the left. So it's kind of like I take the top shape and translate it along a vector to reach the bottom shape. So we only end up with a total of one axis of symmetry on this shape, or one line of symmetry. So that's going to be right down the middle here. And on our trapezoid, similar to the parallelogram, if we cut down the middle, we get 2 equal halves, so that's one line of symmetry. We'll find the exact same kind of stuff. If we cut through the diagonals, if we cut through the middle, well, here even the middle is going to give us a smaller half and a bigger half. But there's no other way we're going to be able to create 2 symmetric halves with a line of symmetry. So those are how we find linear symmetry, and sometimes we have just one line, sometimes we have multiple. Our next kind of symmetry we're going to talk about is rotational symmetry. In rotational symmetry, we end up with some center point that things can rotate around. So let's look at some examples. We'll look at the same exact shapes and try to find whether there's a center of rotation and some amount of rotational symmetry. So before you pause and try this on your own, we have 2 keywords here we need to define: order and magnitude. So order of symmetry tells us how many times the shape regains its original orientation throughout its rotation. So let's do one as an example. We'll start with number 1. Our center of rotation would be about here, and we see that if we turn the shape, then this line here at some point is going to reach here. And at that same point, every line is going to overlap with a line that we started with. So we can rotate this shape around, and it's going to regain its original look several times. So if we take this line and rotate counterclockwise in the positive direction, it's going to reach over here, and that will be one time that it's symmetric. If we keep turning it, keep going around, that line's going to come around to here. And then if we keep going again, it's going to get back to where it started. So basically throughout the total 360 rotation, there's 3 times that it regains its original shape or original orientation. So we have, we call this order 3. So this is order of magnitude 3, order of symmetry 3. And then the magnitude is simply the number of degrees we have to rotate to find the next time it's symmetric. So if we said the magnitude is always just going to be 360 divided by the order. So it's kind of redundant. They tell us the same thing. And if we multiply them together, they should always give us 360. So if I divide 360 by my order of 3, that means that from where we started to our second symmetric orientation, we went 120 degrees. Then we went 120, and then we went 120 to return to our original state. So if you have an order and magnitude, they always have to multiply together to make 360, because order is the number of times symmetry is regained, and magnitude is 360 over that number. So now you can pause the video, try the other one, see if you can identify, does it have rotational symmetry at all? And if so, what's the order and magnitude? All right, so number 2, our center would be here. And if we rotate this corner around to this one, then we end up with this corner being down at the bottom, which is different, so that we don't regain our symmetry there. If we keep going and this one goes all the way around to here, we go 180 degrees around, then this top corner will be at the bottom, so still no symmetry. And if we keep going around, we'll get back to where this point is where it started, and we never found a point where everything was symmetric. So this one does not have radial or rotational symmetry. No rotational symmetry. Right? Okay, so number 3, if we have a center point in the middle and we rotate this corner around to here, then it's going to bring that corner there, so everything is going to regain its symmetry to the original shape. So again, we could bring this corner to 1, 2, 3 positions where everything ends up being symmetric. So just like number 1, this one is going to be an order of symmetry 3, and a magnitude of symmetry is 120 degrees. So we have to turn 120 each time to find a symmetric spot. Our square, our center point is right here in the middle. And I think you can guess, like the triangle, if I rotate till this corner reaches over here, then it's going to have a total of 4 times that it regains its original orientation. So we have order of symmetry 4, and magnitude is going to be 360 divided by 4, and hopefully we know that's 90 degrees. So like a quarter turn, like we did rotations, 90 degrees goes from quadrant 1 to 2, 2 to 3, 3 to 4, and then we're back to where we started. Okay, number 5. So this one we said didn't have linear symmetry or line symmetry, but it does have rotational symmetry. So if I take this little foot, for example, and I rotate it around, it reaches this foot, and then each foot reaches the next spot. So his symmetry, we have position 1, 2, then we rotate 2 around to 3, and we keep rotating around. We have 4, 5, 6, 7, 8 total positions where we regain our symmetry. So we would call this an order of symmetry 8, and the magnitude of symmetry would be 360 over 8, which should be 45 degrees. So remember, we're just taking 360 over 8, and basically if you think about it like the square, we had our 4 cases here, and then an extra 2, or an extra 1 in between each. So we have 8 spots. Okay, so next one, we said there was a line of symmetry here, but if we rotate the shape, if I turn this corner up to here, it doesn't match up, right? I'm going to end up with a tall shape instead of a wide shape. So if I rotate this corner all the way around to here, then the shape is going to be back to where it started, because this corner and this corner have traded places, and this corner and this corner have traded places. So here we only have an order 2, and our magnitude is 180 degrees. Our last one, the trapezoid, our center would be in the middle here. And if I rotate it, I have a long side and a short side. So these are never going to find a spot where we can overlay the rotation to create the shape we started with and regain that symmetry. So this one is none. Let me go back to the slide here, and we can actually look at rotating these. So this one we talked about starting here, we rotate around. Now we're back to where we started here. That's position 2, that's position 3, and then back to where we started. So we end up with that degree 3. This one, there's nowhere we can turn it where the 3 points line up the same way until we get back here. So that one has none. This one, we said if we do 180, we're going to end up with the shape we started with. So right there is our parallelogram the way it started. So you get the idea. If we have a kind of digital version or draw this on like a paper, we could rotate it around and see when it becomes the same as its original shape. So our next topic is three-dimensional symmetries. So we have a couple types we're going to talk about. The first one is very similar to the line symmetry, but we call it plane symmetry. So instead of a two-dimensional shape that's symmetric across a line, now we're going to talk about a three-dimensional shape that is symmetric across a plane. So it's still a reflection, just like line symmetry was. There's still this thing cutting through the middle, except now the thing cutting through the middle is not a one-dimensional line, it's a two-dimensional plane. The other kind is called radial or axial symmetry, and it is created by revolving a shape or rotating it around a central axis. So think of a donut or a bagel or something round like that, or a ball. Those have radial symmetry. Rotational is two-dimension, radial or axial, or the textbook calls it axis symmetry. I don't like that one. But this kind is a three-dimensional version of rotational symmetry. So we have some shapes here. Let's look at each of these. This one is a ball. So we want to look at, does it have radial symmetry? This should say radial, not rotational. And we want to identify if it has plane symmetry or radial symmetry, what are the planes or axes of symmetry? So number one, if you think about it, can we cut through it somewhere with a plane and create two equal halves? So this is a sphere, and we've learned before that hemispheres are just half spheres. So I could cut through the plane where this pink line is shown, and it would give me a top half and a bottom half of this ball that are identical. But I'm not limited to cutting a plane through in that direction. So if I took a plane and cut through this way, I would end up with two hemispheres up here and down here. If I cut through here, I would get a left and right hemisphere. So just like the globe, we could cut around the middle and have a northern and southern hemisphere, like this pink line, or we could cut through the other way and have an eastern and western hemisphere. But there's not limited to those cardinal directions either. I could make a plane through at any angle. So basically, a sphere has infinite planes of symmetry. I could cut any plane as long as it goes through the center point of the sphere. It's going to split the shape into two equal hemispheres. So it does have planes of symmetry, and it has infinitely many. So kind of likewise to that, if I look for an axis of symmetry, if I make an axis of symmetry through the middle, then everything around it is equal. So think of the axis the Earth rotates on. We have a specific axis for the way the Earth rotates, but I could draw an axis through the center of the sphere going at any angle I want to. So I, just like planes, am going to have infinite axes of symmetry that I could revolve the shape around, and it would be symmetric. So a sphere is super, super symmetric. It's very symmetric. Okay, next one we have here, this L-shaped block. So if we were to cut a plane, this is going to be hard to draw, through the middle right here, like that. Basically, we could cut through with a knife, like top down, and split it in half, kind of like cutting bread, right? We're going to cut it into two parts. So if I have a bagel and I want to cut the bagel, I want to cut it into two equal halves, I pass a knife down through the middle. So same idea here, we can split this right down the middle. We end up with two equal halves, one in the front, one in the back. But that is the only plane of symmetry that we're going to be able to find. If we move that plane backward or forward, then we end up with two unequal slices. We get a thin slice and a thick slice. If I try to turn the plane and go through any other direction, then I don't have symmetry because I have this part sticking out here and here that are going to make it, so say I cut through a plane this way, like front to back, then I'm going to have this bottom half and then the top half, and they're different shapes. So here we have plane symmetry, and we only have one plane of symmetry. We don't have any rotational symmetry on this shape. So if we try to spin this shape around, there's no way that we can spin it that's going to be recreate this shape. And then with a cone, we have, similar to a sphere, I could cut through a plane of symmetry this way through the middle, and I'm going to end up with two half cones. But again, I could rotate that plane and cut through this way, and I'm going to end up with two equal cones as well. So kind of like the sphere, I have infinitely many planes that I could cut through this, as long as they all are perpendicular to the cone, like going straight up and down, and passing through the axis of symmetry in the middle here, then I could have as many planes as I want that make a symmetric cut through this. But if we look at radial symmetry, there's only one axis through the middle here that goes through the center of the circle and the point of the cone. This is the only axis where everything remains the same by revolving around. So if you think about, if I try to pass an axis through this way and we spin the cone around it, it's not going to be spinning nice and evenly. It's going to be wobbling around that axis. So we only have one stable axis that this will spin around and retain its shape all the way around. So those are our types of symmetry. Just to review them real quick, we had line symmetry, where we were looking at a line of symmetry that makes two equal halves. You may also have seen that in science as a type of symmetry called bilateral symmetry. The difference with bilateral, it's more limited because it's only where you have a single line of symmetry, like number 2 here. But with line symmetry, we can have like the triangle and the square, where there are multiple lines of symmetry in one shape. Rotational symmetry, that's one where we can rotate the shape and regain its original symmetry throughout the rotation several times. So here we had, remember, 3 times that we regain that orientation. And then we had our 3D symmetries with plane and radial symmetry. So these are the practice problems. They're on Canvas. Work through those, and you should have it down.